Hey, I want to talk to y'all. I like being right up front with everybody. I'll be real with you guys because you guys are real with me, and so I just share. I know that there are things that happen outside of our virtual classroom that affect our virtual classroom, and this is one of those times for me. So I'm sharing with you because you guys share with me when you are having extra struggles and things that affect life here, and I want to do the same thing. So I had a lab result come back last week. I know a lot of y'all know because you've had me before. I know I've talked about it a lot this year. But several of you know that I have had leukemia in the past. 3.5 years ago, I had a very aggressive, very life-threatening leukemia that caused me to have to be out of school for over a year at the time. Once they finally figured out what was going on, it took a while, and I was 105 days in the hospital, in and out. I had to have a bone marrow transplant, so that way I've got some bone marrow inside of me from like a 27-year-old dude in London. So I make his blood instead of my blood, and that's what it took to cure my leukemia. I had a blood test come back last week that gives a hint that my leukemia might be returning. In that case, what has happened, if that is true, is that whatever little bit of my bone marrow remains has been strong enough to fight back and try to take over more of my body. Generally, the new bone marrow will kill out whatever's left of my bone marrow. But at this point, it doesn't look like that's happened. And we've had one test result that has hinted otherwise. So I had some blood work done last week to try to verify that, but it takes like a week and a half, 2 weeks to get that result back. And so we're waiting to see. Right now, I have no idea what it means. It showed just a very, very like one blood cell out of every 10,000 looks like it has leukemia. Very, very small trace amount. So I don't know what the path is at that point. I may just have to go back on a chemo pill to fight that. I'm hoping I don't have to go back to the whole bone marrow transplant path because that is really nasty. But I am having symptoms that mimic the symptoms I had 3.5 years ago, which is a lot of joint pain. Like last Friday, I did not come to school because I could not hardly walk. My hip hurt. It felt like really bad arthritis in my hip where I couldn't move my hip without a lot of pain. And there was even pain when I wasn't moving my hip. It was not a comfortable position anywhere. And it's also been in my back and my shoulder blade. And so I'm just having lots of joint pain, which I had last time. So that's kind of another indication to me that we are having something going on. So I just want to let you guys be aware because, I don't know what's going to develop into, but things happen and life happens. And so I share with you when life happens because you never know who it might affect and what might become of it. So as always, I keep it real. I'll keep up, guys. I'll share my life with you because I care about you guys. I care about your success, and sometimes your success relies on me to be here. And just letting you know, there may be some doctor's appointments and times when I may be as have a little availability compared to now, but I'm hoping it's not anything drastic. So we will move on from that. So today, let me look at what we're doing in Algebra 3 this week. So today in Algebra 3, looking to see where everybody is. Got a few people that have not got caught up on lessons. You should have turned in 3.03, 3.04 yesterday. The result was due last night, 3.03, 3.04. And then this week we have 3.05 and the quiz. 3.06 is a quiz over the first 5 lessons. So we have that coming up today that I will talk about 3.05. The quiz, I'm not really talking about that. It's just over these first 5 lessons. So if you've read the first 5 lessons, tried the practice problems in there, and know how to do the practice problems in the lessons, then you probably had no problems with the assignments that followed those and can do well on the quiz. So I won't spend a lot of time on that. We'll go over lesson 3.05. And 3.05 is over solving polynomials. And you're like, okay, no big deal. That's what we've been solving for years now. We're in algebra 3. Yeah, you start out solving like linear equations. All right. 3x plus 5. What does x equal? And so we did solving of linear equations. And you did that for years. And then we moved on to quadratic equations. If you've got x squared plus 4x plus 4, what's the solutions? And we know quadratic equations can have 2 solutions, right? And now, thanks to the fundamental rule of algebra, we know it does have 2 solutions. And they're either positive, negative, or they're complex, where they may be imaginary numbers. But we know how to solve quadratics. So we have the quadratic formula. If all else fails, we can just throw out the quadratic formula and find out the answer. But today, we're not talking about linear or quadratic. We're talking about solving polynomials. We're talking about like bigger than quadratic. So I'm going to work an example with you today because lesson 3.05 has several examples. When you go through this lesson, do it purposefully. Have a pencil and paper in front of you. It's only 6 pages, but there's a lot of problems in there because these problems take a lot of work. We're going to do a problem here together, and I want you to see how much work this takes. And let me just tell you, if you just look at it on the screen, I'm going to go through the lesson. I'm going to click, and we'll sit here. Okay, I see that. All right, I see that. I say, all right, next page. Okay, I see what they did. Okay, next page. And you just go through the lesson, right? Just like I'm doing. Just sitting there, looking. And then you go try one and the problem. And the first time you really try one is maybe on the test, maybe that show your work part or a quiz. And you're like, oh, okay, I remember, we did this. I think we did this. What else did we do? Unless you practice, unless you go through this lesson with pencil and paper and try those things before you look to see their answer, unless you practice this, you're not going to be very good at it. This is a lot of steps, a lot of work. And the more you practice this, the easier it gets to where I can just hand you a problem and you can just go through the steps and do it because you've practiced it enough. The way you learn math is you do math. If you're not doing math, you're not learning math. You're watching other people do math. You have to do math to learn math. So this is one of those lessons that's really important to have pencil and paper. And when that lesson puts that problem up in front of you, you need to write that problem down, and it says, okay, now use the fundamental theorem of algebra to figure out how many roots that'll have. You try to write down how many roots before you click on their answer. Okay, what are the possible rational factors of this? You need to figure out all the possible rational factors before you click on that little tab and it tells you what the rational factors are. You need to be doing it ahead of the lesson and not just waiting on it to tell you all the answers, because that's how you're going to learn this. So let me put my screen up. We're going to walk through an example together as a class. Oh, apparently today's National Chocolate Cupcake Day or something. So listen, I'm going to move that out of the way. Save that for later. We've got cupcakes here today for National Cupcake Day. I did not know it was National Cupcake Day. They have all kind of days that I don't know about. So, all right. So now we're saying, what if I ask you to give me the solutions for x to the fourth minus 9x3 plus 15x squared minus 9x plus 14. Great. Give me the solutions for that. Right? We know what gives the solutions are. If I gave you, given the solutions to 2x plus 4, you would figure out what x equals. It means that is the x that makes that equal 0. That's a root. That's a solution. That's a 0 for that. All right, so if I ask what are the roots, what are the solutions, what are the zeros for this equation? All right, so we need to know how to do that. So what we have to do is we have to use the things that we know. And our lesson talks about right off the bat. I have to combine too many different things at the same time. Our lesson talks about the 5 things you need to review and understand how to use. Right on the first page, it says review the fundamental theorem of algebra, the rational root theorem, Descartes' rule of signs, the remainder theorem, and the factor theorem. And we're going to use all of those in solving this right here. So first we use the fundamental theorem of algebra. And the fundamental theorem of algebra says, well, the largest exponent we have is x to the 4th. So that means there are 4 zeros. There are 4 solutions. There are 4 zeros because the fundamental theorem of algebra tells me that, because this is x to the 4th. All right, now I'm going to use the rational root theorem, the second one it says, and say, what are the possible rational roots? Rational roots. Well, if you remember the way we did that, as we said, what's the coefficient of the first term? Well, it's just a 1, right? And then what's the constant? 14. And so we called this P, we called this Q, and we said all the rational roots are the P's over the Q's. Well, what's really nice here is our Q is 1, so we don't have any fractions. It's just all the factors of 14 over 1, which means it's just the factors of 14. So what are the factors of 14? Well, plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. These are all the numbers we can use to multiply together to be 14. 1 times 14, negative 1 times negative 14. 2 times 7, negative 2 times negative 7. So plus or minus 1, 2, 7, and 14. Over here, we just have 1. And the only factors are 1. So it'd be over 1, but we don't write over 1. It's just these. So this one's not too bad. This one's not too bad because there's only 8 numbers that could be a rational root. That's it. So we've used the fundamental theorem of algebra, now the rational root theorem. Now we're going to use Descartes' rule of signs. And that's going to tell us how many of these are positive, possibly positive real roots, and negative real roots. Negative real roots. And then after we know that, that will tell us how many complex roots. Oh, there's an M in there. Complex roots, which means they're imaginary. How many positive real roots, negative real roots, and then imaginary roots. This is using Descartes' rule. Remember what Descartes' rule says. How many sign changes are there? This is positive, that's negative. That's 1 sign change. That's negative, that's positive. That's 2 sign changes because it changed again. Positive to a negative, that's 3 sign changes. Negative to a positive, 4 sign changes. So there's possibly 4 positive real roots. Remember, if there's 4, Descartes' rule also said we could end up subtracting 2 because maybe 2 of them have imaginary numbers. Imaginary numbers always come in pairs. So we would never subtract 1, it's always 2. Or there could be 2 sets of imaginary numbers. Whenever you find out how many positive real roots are, it could be that, or 2 less, or 2 less, or 2 less. If this was 6, we could go down again. 6, 4, 2, or 0. Subtract 2. Okay, negative real roots. So let's see how many negative. I want to put another piece of paper up here because I want to get back to this equation. To figure out how many negative roots there are, according to Descartes, is we substitute negative x. And that tells us the negative roots. So negative x to the 4th minus 9 times negative x to the 3rd plus 15 times negative x squared minus 9 times negative x plus 14. So let's simplify that. If we have a negative number taken to a positive even power, right? It's taken to an even power. It means it's a negative times a negative and a negative times a negative. 4 times. That's going to make that a positive number because anytime you have 2 negatives multiplied each other, they're positive. You have another 2 negatives, they're positive. So this is going to be positive. So this becomes x to the 4th, positive. If we have a negative number taken to an odd power, it's going to end up a negative. So this is negative 9 times negative x to the third. So negative times negative makes that a positive 9x to the third. Again, negative x times negative x makes that a positive x squared. So it's 15x squared. This is a negative times a negative. Makes that positive 9x plus 14. All right. So now how many sign changes do we have? Now we simplified that. Positive, positive, positive. So far the sign has not changed. Positive, there are 0 sign changes. The sign never changes when we substitute negative x in there. So that means how many negative real roots are there? None. We just ruled out half of the possible rational roots that we had because we cannot use negative 1, negative 2, negative 7, or negative 14 because Descartes' rule tells us there are none. We don't have to worry about testing any of those. All right, so complex roots, how many are there? Well, if there are 4 positive roots and no negative roots, that doesn't leave any for any imaginary roots because there's only 4 total, and they're all 4 right there. But if there's only 2, and we know there's no negative, that means there could be 2 complex roots. Or if none of those are positive, that means all 4 of those are imaginary complex roots. So this is our only possibilities. There's no negative at all. We either have 4 and 0, 2 and 2, or 0 and 4 for our roots. All right, so now we have to use the remainder theorem and the factor theorem. The remainder theorem tells us if we're only testing the positive ones. If we take the 1, because we're testing that, we use synthetic division to divide it into this, right? We're just going to use the coefficients with synthetic division. I mean, you can do it by long division if you want to. If you want to take x minus 1 and divide it into that with long division, feel free. I'm going to use synthetic division. Coefficient of 1, coefficient of negative 9, coefficient of 15, coefficient of negative 9, and 14. So if I divide this in here, the remainder theorem will tell me what the remainder is if I divide this in there. The factor theorem says if the remainder is 0, then this is a factor of this polynomial. And that's what I'm trying to figure out. Is this a factor, which means it is a 0, it is a solution. All right, so we always drop the first one down. The 1 just comes straight down. Multiply. 1 times 1 is 1. Then we add. Negative 9 plus 1 is negative 8. Multiply. Add. Multiply. Add. Multiply. Add. Okay, the remainder is 12. This is not a factor. Okay, so right away we know 2 things. We know 1 is not one of the rational roots. So we also know there can't be 4 because there's only 3 left. So there's either going to be 2 positive roots or there's not going to be any positive roots because we only had 4 choices to start with, and 4, 2, and 0s are only choices. So right now, there's not going to be 0 complex either because there's either going to be 2 or 4. So let's try the second one. Let's try 2. So again, the same coefficients, negative 9, 15, negative 9, 14. Okay. The first one comes down. 1. 2 times 1. Add negative 7. 2 times negative 7. Add, that's 1. 2 times 1. 2. Add negative 7. 2 times negative 7. Oh, the remainder is 0, which means this is a root. That means x minus 2, since this is a 2, 2 minus 2 would be a 0. 2 is a 0. X minus 2 would be one of the factors of this polynomial. So here's a shortcut. We can now call this a depressed polynomial, not because it's sad, because we've depressed it. We made it smaller than this one, because now we know that we can break this out as x minus 2 times, when we divide an x minus 2 out of it, this is what's left. And now since the other one was x to the 4th, this is now x to the 3rd. So it's just 1x to the 3rd minus 7x squared plus x minus 7. we've broken this down into these two factors now, because we know this is one of the binomials that can divide out of there, because 2 is one of the roots. So since that is true, we know that this is not true. There has to be another root. There has to be another root, which means there's not 0. And we know it can't be 1 or 3. So that one of these other ones has to work. But 2 works. The positive 2 works. So there's going to be 2 real and 2 positive, 2 complex. Okay. Now let's check 7. And we can divide 7 into this now, because this is all that's left. We don't have to go back to this original one. We can use this. So there'll be 1x to the third minus 7x squared plus 1x negative 7. Remember, if one of these was missing, we'd have to have a 0. Like if this was gone, it was just x to the third minus 7x squared minus 7. We'd have to have 0x. You got to have the coefficient for every term, starting with the big one. Okay, first one comes down. 1 times 7 adds together to 0. 0 times 7, 0. Adds together to be 1. 1 times 7, 7. Remainder of 0. So 7 is also a root. 7 is also a root, which means we don't even have to check 14, because there's no way it can be one. There's only 2 positive roots. Can't be 3. So now that we found both of them, it only took 3 times dividing. We had 8 options to start with, but using what we know from these other theorems, we were able to rule it down and only had to do it 3 times instead of 8. So, all right, so now we know this is x minus 2 times x minus 7 times what's left. This started out as x to the third, so this is x squared. There are 0 x's, so I skip that, and this is the constant, plus 1. So now we've taken the original polynomial up here, and we have factored that to be this. So we know the solutions are 2, 7, and what are the 2 imaginary solutions? Well, we have to figure out based on this last binomial over here. So if x squared plus 1 equals 0, right? Because that's the other zeros, the other solutions. Subtract 1, x squared equals negative 1. We're trying to solve for x. So if we have x squared, we're going to take the square root, both sides. X equals, when we take the square root, it's plus or minus. Square root of negative 1. Well, that equals I. So the other answers are I and negative I. So this is our 4 solutions. Fundamental theorem of algebra said there are 4 zeros. There are 4 solutions to this polynomial. And here they are. 2 times 7 times I and negative I. All of those 4 roots. And we can write this new polynomial. We can write the exact polynomial as its roots. X minus 2, x minus 7, x minus I, and x plus I. That's the exact same polynomial as the top. We just wrote it in its factors. Just like if we had the number 12, we can say it's 12, or we can say it's 2 times 2 times 3, right? Because 2 times 2 is 4, 4 times 3 is 12. We can say it's 2 times 2 times 3, or we can say it's 12. We can say this is x minus 2 times x minus 7 times x minus I times x plus I, or we can say it's this. So taking a polynomial, finding the 4 solutions to it, the 4 zeros that it has, that if any of these are put in for x, that entire polynomial will equal 0. All right, that was one problem, guys, one problem. Unfortunately, we know a lot of things with those 5 different rules and theorems that we've been studying this unit to be able to narrow this down, because this could have been a lot more work if we were checking all 8 of those. And fortunately, we knew how to use the rational root theorem in order to narrow it down to just 4. Otherwise, you're just guessing numbers. Right? And this one wasn't so bad. If this would have been a 2x to the 4th, then we'd have 1 over 2 and 2 over 2 and 7 over 2 and 14 over 2. All of those, you got to add those extra possibilities in there. because you'd have another round of numbers to go through. But this one, which is having an exponent of 1 up here, made our P over Q the 1 on the bottom. So this is why I said it takes practice. We had to go this extra over here where we had to find the negative roots. This takes practice to be able to do this consistently, guys. Practice, practice. Let me show one other thing that we talk about in this lesson. This is one big part of it. But another part of it is, what if I said, I want you to write the polynomial and I'm just going to give you the roots or the solutions. And I said, one of them is 2, but it has, and I'm going to say a multiplicity of 2. And the other root is 3i. That's what I told you. This is the solution. This is the roots of this polynomial. Now you write the polynomial. Okay, you're like, okay, well, what does this mean? Multiplicity of 2. Well, that means there's 2 of those. So that means actually the roots are 2 and 2. But we just say it's a multiplicity of 2 because I said, what's the solutions? You would say the solutions are 2, and you wouldn't tell me 2 twice. Say, what's x equal? X equals 2. What else could x equal? X equals 2. No, you already told me that one. It's just a multiple answer. That's what I mean. It's a multiple answer. We have more than 1 2 in there. So multiplicity. I could have a multiplicity of 3. Maybe there's 3 2s as an answer. So you're like, okay, well, I've got 3 roots. No, you don't have 3 roots, because remember, anytime you have a complex imaginary root, they always come in pairs. So you've got negative 3i as well. If I tell you this one, you have to assume you have this one. And this is really 0 plus, because all complex numbers have a real part and an imaginary part. So if I just give you an imaginary part, that means the real part's 0. Real part's 0, so you don't have to worry about that. You just have the 3i and the negative 3i. So if these are the solutions, these are the roots, for you to write the polynomial, you need to do this. First, write the polynomial with its roots. Oh, let me put a minus in there. If the 0 is 2, then it's x minus 2, right? Because 2 minus 2 is 0. Over here, if it's 3i, then it's x minus 3i. And if it's minus 3i, then it's x plus 3i. Okay, so here's the polynomial written out as its roots. But I didn't ask you for the roots. I asked you for the polynomial. So you need to start multiplying these together. X minus 2 times x minus 2. So that's going to be x squared. Negative 2x and negative 2x is negative 4x. And then negative 2 times negative 2 is plus 4. So those two multiply together is this. This is, if you remember what the difference of squares is, this is going the opposite direction. This is the difference of squares when they're put together. X squared minus 9i squared. Because the middle term will drop out. You'll have negative 3ix and you'll have positive 3ix. And so the middle term disappears. This, if you have negative 9 times I squared is negative 1. I times I is negative 1. Don't forget that rule. So that means this is plus 9. So what you have is x squared minus 4x plus 4 times x squared plus 9. Ah, look there how our imaginary part of our polynomial goes away. There's nothing imaginary about this. When I get to our final polynomial, we should not have an imaginary component left. It has gone away. Then you have to multiply these together. So you would distribute, you can distribute this into both of those 3 times, or you can distribute the other direction. Doesn't matter which way you multiply. 2 times 3 and 3 times 2 is the same answer, right? But when you multiply, and I'm not going to work all that out because you guys have distributed before, you can work that out. It's going to end up x to the 4th minus 4x to the 3rd plus 13x squared minus 36x plus 36. That's what the two multiply together. So if I gave you the 2 with multiplicity of 2 and 3i, you would need to find the polynomial that those are the roots of, which is right there. Got to put it all back together. Make the X look like an X. There you go. Put it all back together. So that is what we're looking at this week. Problems that are a full sheet of paper. Problems can take a lot of work also to go the other direction. Be able to find the zeros, positive, negative, and complex. Takes a lot of practice to do this well. Way you learn math is do math, right? So do the math, guys. Go through the problems. Go through the practice problems. Don't cheat yourself. Don't just watch somebody else do the math. Do the math yourself. And then you shouldn't have any problem. You get to the test, you'll know this. And it'll help you know those theorems too. The fundamental theorem of algebra, the rational root theorem, Descartes' rule of signs, the remainder theorem, the factor theorem. The more you use those, the easier they get too. So we're learning a lot in this polynomial functions unit. And so good stuff. So we have this lesson and you have the quiz this week, right? Then we'll have another lesson next week and I think the practice test. And then we're going to get to that discussion-based assessment that I've added for this unit. And that's where we spend time one-on-one, probably do it during class or some breakout rooms, may schedule some times during flex if you want to do it then, to where I ask you questions and you explain to me. I may say, how does Descartes' rule of signs tell us how many negative roots there are? If you can tell me the proper way to do that, all right, you get points for that. And I'll ask you another question, the factor theorem or something. I'll just ask you different things from this unit. What would you need to do? I may show you a problem. What would be the first step to this? Or just walk me through the process of how I would do this. So that's another reason to practice this. Because if I'm asking you questions, unless you've practiced it, you're not going to remember. You're not going to know just watching someone else do it. Practice, practice, practice. All right. If you guys have questions, hang around. If you have over a 70, have a great week. Otherwise, I'll see you on Wednesday. And I will be here if you have any questions.
Let's get out of here. Word to your multiples. Math, baby.